Alright, hi guys. So this video is going to be sort of a crash course, if you will, on the decibel scale for those of you who maybe have never seen it before. And in addition to that, I'm hoping to keep this pretty short, so maybe if you've used it before but you've just kind of taken a semester away or been on co-op or something like that where you weren't using it, hopefully this can kind of help you get back into using the decibel scale and remembering what it is and why it's useful. So, first of all, what is it? If you're completely new to this, basically the decibel scale is a way to visualize really small to really big numbers on the same plot. It is not a unit. That's a common misconception. It's actually just a ratio, and I'll show you that later when we show you the actual formulas that you're probably going to be seeing in E2. But basically, it's comparing some quantity to a reference quantity. And so you can add a unit onto the end of it, like you may every now and then see something like dBV for voltage or something like that, but right now we're really not going to get into that. That'll be something that you might see later in industry or something. But let's kind of talk about, okay, so you know what it is now, kind of. Why do we use it? Why do we need it? Well, I think if you're seeing this video, you've probably already taken Electronics 1. You're probably watching this in Electronics 2. And if you've taken Electronics 1, you should be familiar with, kind of some of the really crazy gains that you can see from an operational amplifier, which is one example of an application where a dB scale is going to be useful to you. And you should kind of be able to think back in your head, okay, yeah, if I were trying to plot, the input voltage on something and then the output voltage, where the output voltage is going to be just huge orders of magnitude, thousands of times greater than the input voltage, it's going to be really hard to plot that on the same graph in a way where you can still see all the detail and have it really actually be a meaningful representation of that information. And so that's one reason why we want to use it, just because it makes things easier to see. Another reason is people are honestly just really bad at kind of thinking about things when we're talking about not just linear changes, but changes by orders of magnitude. So a pretty popular example of this that you probably have seen at this point is when people talk about, the amount of money that Jeff Bezos or Elon Musk has, for example, where we're talking about billions of dollars, and how if you were working the average American worker and got the average American worker's salary, which at the time of the article's publishing was, a little higher than 45K, it would take you about 2.8 million years to accumulate the wealth that Jeff Bezos had at the time that that article was written. So that just kind of is one way that you can illustrate how it's kind of counterintuitive when you're talking about changes of orders of magnitude for people, that they just kind of can't conceptualize it. And so that's where having the decibel scale, again, is kind of useful, because it's talking about the change in orders of magnitude rather than having it simply on a linear scale. Okay, so we talked about two good reasons why we want to use the decibel scale. So let's actually look at some of the formulas that you're probably going to see in this class so that you can kind of try to tie it into what you're learning in this course. So the first formula that I think you're probably going to end up dealing with the most is where you have the magnitude in dB is equal to 20 log of V in over V out. And that is, as I was saying, where dB is really a ratio of two things that you're comparing. It's not a unit, so you're comparing the V in and the V out.
Another way that you could look at this, depending on, what information you have available to you, what you're measuring in the lab, you might also just do the same thing, but you might take the current in over the current out. And um, lastly, you're probably not going to see this equation so much in E2, but it's useful to just kind of understand, you know, there's this 20 hanging out in front here in both of these equations. What's up with that? So for the power application, you have this last equation here, and you've got a 10 out in front. Well, decibel came from a unit bell, and obviously the deci in front of it is the prefix indicating that 10 in front of that log there. And that makes sense. Okay, we're used to prefixes here, but how did we get from the 10 to the 20? Well, I don't know about you, but when I was first learning about the decibel scale, it had been a minute since I had taken algebra and was really actively using logs a lot. But if we can, harken back to those days and try to remember some of those properties, we can look at the power rule right here, and that's actually telling us that when you have something raised to some power, you can actually bring that power out in front of the log to make your life easier in some cases. So between power and current, or power and voltage, we all remember our basic circuits. So power equals I squared R, or V squared over R. And so you're just taking that exponent out to the front in front of the log. And that's where you get that 20. Now, another interesting property of logs is this first one right here, the product rule. And this is actually probably going to comprise the third and what I think might be the most important reason why we want to use a decibel scale versus a linear scale. And in order to illustrate this, I'm going to take you down and we're going to walk through a little example here. So let's say we have this cascaded op-amp configuration right here. And let's say, just to keep this simple and keep the numbers from getting too crazy, that each stage of this op-amp is going to have a gain of 100, right? Totally reasonable, totally something that you've probably seen in E1 as, a gain on an op-amp. And so you've got your V in here, your V out here. Excuse my handwriting, this pen is kind of new to me. And okay, we want to get the gain between V in and V out. And well, in order to do that, where we've got these three different stages, we're actually going to have to multiply these stages. And that's going to take you all the way to saying that V out is equal to 1 million V in. Now, I don't know about you, that is already kind of a big number to me. And if a professor said to me, okay, I want you to plot the gain of this circuit that we're looking at here, and we were talking about it in kind of this linear way that we're thinking about from E1, I don't even know how I would begin to plot a gain of 1 million on a linear scale. I just don't want to do it. It sounds gross. I don't see how it's useful to anybody because it's not going to convey information in a meaningful way that's readable to normal humans. So that's where that property that I was just talking about of logarithms, that product rule, comes in really handy and makes the math on this a heck of a lot cleaner. So I'm going to take you through in a second how to quickly convert between linear and decibel, but for the moment, just trust me when I say that each of these stages is going to give you a gain of 40 decibels. Now, when you're taking the gain in decibel, instead of multiplying as you did in the first example where you're using the linear scale, you're actually just going to sum everything together, and that's going to give you that in a dB scale, V out is equal to 120 V in, which is a heck of a lot easier, if you ask me, to try to plot that on a graph in a meaningful way.
All right, and then so the last thing that we're going to talk about here is just how to kind of quickly work your way through converting, like I did here, from the linear to decimal scale. Because when you're doing this a lot, it's certainly handy to be able to do this kind of off the cuff without having to put everything into your calculator. So, and I'm hoping we're going to be able to put a timestamp in the description on this so that if you've actually seen decibels before, you don't have to listen to me rambling for 20 minutes or whatever it's been already. So basically, if you've got some number, let's take, get my pen going here again. Let's take something really big, something, again, that I don't want to be plotting in a linear scale. 1 million. Now, in order to convert that to a decibel scale, all you're going to have to know is that for each place, so I'm talking about like tens, hundreds, thousands place, you're going to add 20 dB, since from these properties we were talking about, it's additive, not multiplicative. So you're going to just count. It's 20, 40, 60, 80, 100, 120. So that just gives you, pretty quickly, 120 dB. Easy, right? And you can do the same thing if you've got really small numbers, because we also use decibel for really small numbers, even though I didn't personally take you through that. But here we're just going to say, all right, that's negative 20, negative 40, negative 60, negative 80 decibels. Oh, forgot my 0, but negative 80 decibels. Easy, easy peasy. And that also hopefully kind of gives you an idea of why you're seeing 20 dB, 40 dB over and over and over again in E2. It's mostly because of this, honestly. One more thing, I am actually adding this back in. I realized when I was editing this that I missed something that I wanted to point out is if you are like me and you have a TI-89, you are not going to have a regular, like the, where's my pen? Let's see, log base 10 on your calculator. You're only going to have a natural log, and so you're going to be needing to use this change of base rule, which I'm sure we've all used before, but again, it's probably been a minute since you've taken algebra, and I don't blame you if this wasn't immediately on the top of your head. So you're just going to use the change of base rule if you're trying to use your TI-89 to use a log base 10, since you've only got the natural log on there. Otherwise, honestly guys, you're going to be using MATLAB in this course and moving forward a lot, so you can just do your homework in MATLAB. It's a lot easier that way. And I believe that is going to actually take us to the end of the video. So thanks guys.